Hi, I'm Imtiaz Ahmad from Indiana University, and I will be presenting our joint work with University of Pittsburgh that explores how IoT devices can be better designed to help bystanders maintain their privacy. IoT devices have become an integral part of our modern lives. Equipped with many useful sensors, these devices continuously collect various types of information from us. However, this very nature of IoT devices has some serious privacy implications. Here we see some examples of privacy breaches that have been reported in the media related to unexpected audio and video recording by these devices. This situation is even worse for bystanders who are not owners of the devices. For example, there is no way for a bystander to know if a camera is actually off. This ambiguity creates an uncertain sense of privacy for bystanders. In general, the current sensor design space lacks effective and meaningful feedback about whether a sensor is actually off. So how can the sensors effectively communicate their off state to people in the vicinity? Well, for a camera, such feedback can be easily conveyed by covering the lens. However, things get tricky when it comes to microphones. Back in the day, devices had external microphones, and one could be assured that the devices were not eavesdropping by simply unplugging them. But today's devices have embedded microphones, and often there is no tangible way to communicate their off state. Hence, today's sensors need to be better designed for providing a tangible and more assured sense of privacy, which is the motivation of this study. To be able to better design the sensors, first, we need to understand bystanders' perception of how and when IoT devices collect their information. Secondly, we need to understand the privacy-enhancing behaviors bystanders apply to maintain their privacy. To answer these questions, we conducted an interview study with 19 participants where we showed them two prototypical IoT devices, an Amazon Echo Show and a Nest Indoor security camera. Based on our findings, we identify and define tangible privacy mechanisms as those privacy control and feedback mechanisms that can be manipulated or perceived by touch and also provide high assurance of privacy to the users. Next, we highlight some of the key findings from this study. Due to the lack of meaningful feedback, in certain situations, our participants were uncertain about a device's state. For example, when talking about the Echo Show's off state, they were uncertain if the device was actually off or in an intermediate standby state still capable of recording. Our participants expressed a lack of trust with software controls, and they trusted hardware-enabled on-off buttons, saying it gives them their desired control over the devices. We also found that the perception of a device is mostly guided by its primary function. This heuristic is particularly dangerous because thinking that an Echo Show's primary function is to verbally communicate with the user and not to watch them like a security camera, many of our participants went as far as placing one in sensitive places like their bathrooms. Next, we highlight some key design recommendations that emerged from our interviews. IoT devices need to have simple and reliable physical off buttons as opposed to multipurpose buttons. For example, a single push of this button on Facebook's portal device merely turns the display off instead of shutting it down as with a long press. Thus, we advocate the inclusion of simple and old-fashioned switches that break the circuit while providing a tactile feedback. Probably the most tangible way to assure people that a camera is not watching them is to use a lens cap or a shutter. However, to be truly in line with the recommendations of tangible privacy, the lens cap or shutter needs to be controlled manually. For disabling microphones, the current tangible practice is the use of a mute button. But to provide strong assurances of privacy, this button has to be a hardware switch that can physically disable or disconnect the microphone circuit. Apart from these, prior studies have blocked microphones by jamming them using ultrasound. We recommend that this approach needs to provide some form of tangible feedback so that bystanders can be assured that the jamming is actually taking place. And yet another possibility is the use of detachable sensors. Plugging out a camera or microphone module from the device would give the user a strong tangible assurance that the device is not watching or listening. In conclusion, we showed that bystanders have unique perceptions of IoT devices and how the current designs of these devices fall short in providing a tangible sense of privacy to them. To address these concerns, we advocate the notion of tangible privacy and propose several design recommendations for future IoT devices. Finally, we would like to thank the NSF for their support. Please feel free to contact us with any questions about the study.